Okay, great. So this is an example of a plunge frozen. Nope. Oh, am I no longer sharing? I don't know what's happening.
The tomography is difficult.
AV sucks. I don't understand. I didn't move it. It should be sharing. Okay, great. Now, hopefully this works. So this is an example of a plunge frozen grid versus a waffle grid. And this is yeast. So one of them was frozen on a GP2 and the other one was an HPF waffle. So you could see how the yeast are all in the square everywhere. So you could basically mill anywhere you want within that square versus the plunge frozen grid where there are clumps and you can mill the clumps, but they're more dispersed and there's less of them. And you wouldn't want to mill near the grid bar. So the clump in the leftmost square on that corner there would be completely unusable. Let's say if that's the only clump that you had. So this is another example of basically the same grids, just in SEM. So on the left here, you have the plunge frozen yeast cells. So that's how the clumps look. And then on the right, that's how the waffle grids look. So you clearly can't really see any of the yeast cells. Sometimes you could see little mounds or little divots within the surface. And you're like, okay, cool, those are yeast. But you really can't tell. You just kind of assume that it's there. Or you could do fluorescence like this beforehand and just make sure all your cells are actually in the squares. Okay, and this is just another view at an angle, just showing the yeast clumps and then the waffle grid. So you could kind of see that there are little dimples in that surface. So those are the yeast underneath. Okay, and finally, not yeast. So these are microsporidia from an actual user. So they did just regular plunge frozen cells, and you can see for B and A on the top, that's how they look. So the lamella were actually extremely small. You could see on the scale bar, the microsporidia itself is a little less than 5 microns. So that lamella is even smaller than that. And it was basically unusable once it went into a cryo. So I'm not even sure it survived until then. And then on the bottom, you can see that we just made a waffle and you could see a ton of microsporidia on that lamella. The lamella is obviously much larger. I think this one's around 20 microns in width. And you're able to get the cells just all over the place within the waffle. So they had preferred orientation. You could see how it all lays on the plunge frozen grid, but then you combat that with the waffle method. So they were able to get different views of this spore thing. Nanotube. They do. All right, this is a gag at this point for this talk, that you could do the waffle method in 11 easy steps, because it's kind of easy, but then it's not so easy because it actually requires a lot of work. So the first part is to polish the planchettes that you're going to use for making this waffle sandwich. So these planchettes look like this. So there's a divoted side on one side and then a flat side on the other side, and not polished with anything on them. They come with these rings around it, and it's just from the manufacturer, I guess, buffering them out. So we want to get rid of that because that will affect what the surface of your waffle will look like, and we want it to be as flat as possible. So basically we just sand them down with a couple grits of sandpaper. So the first one's normally 1200, then we do around 8,000 or 7,000, and then we do 12 or 15,000 for the last step. And you can see just consistently that the surfaces just get nicer and smoother and better. The scratches come out, and that's exactly what we would like, because that will dictate what our surface would look like. And then we normally do metal polish. So this is the one that's now commercially available. The one that we currently use is Pole, but it's discontinued, unfortunately. We thought that one was the better one, but this one probably would work fine. So basically what you do, you just dip the planchette in after it's been sanded down. And then you just kind of move it around in circles on a filter paper or index card or something for maybe 15 seconds. You blot it away, you do it again, and then your surface becomes like super nice and shiny. Okay, and then the next step would be applying hexadecene. So it basically just looks like this, and it's just to make your surface hydrophobic so that nothing actually sticks to the planchettes when you're doing the waffle, because it will come in contact with your sample. Then you just carbon coat the grids with an extra 20 nanometers of carbon. The grids that we currently use are 200 mesh, very important. And then we use just quantifoil 22s, just because that's what we have lying around. So I just carbon evaporate 20 nanometers onto the carbon film side of those grids. And this is just for extra rigidity for when it's actually in the HPF and being having pressure applied to it. Okay, so assembling the waffle. So this is just a little depiction of what's going to happen. You're going to see it later today, but you put in, this is the HPF tip. You put in the bottom planchette with the flat side facing up or your polished side facing up. Then you put your grid in after it's been plasma cleaned for about 30 seconds with hydrogen oxygen on the grid bar side. So the grid bar side is facing up because you're creating like a well for all the sample to sit in. So you apply about 5 microliters of sample. You could probably get away with like 3 or 4, depending if it's like super precious and you want to make more of them. But you just want to make sure that when you apply that top planchette with the flat side facing down, that it kind of just squishes the sample in and some of it comes out, because you ensure that like all the sample has gone into the squares and there's some spillage over. If you don't do that, then you might have air or not enough sample in the squares, and then your surface will be not dictated by that top planchette. So it's going to be whatever the heck it decides to freeze to. I guess maybe the surface of your cells. And then you close it and then you HPF, and it makes a very loud bang. We have a light that goes off now all the time so that people are aware that there may be a very loud bang at some point in time when they pass by the HPF as a warning. So then we clip the grid in this notched auto grid. So this is how it looks. So it normally comes with the notch, the 2 dots on the sides, and then the double dot that's across from the notch, like at the bottom. I Sharpie in the notch and I Sharpie in the side so that you can kind of, I guess, does a pointer work? Ooh, maybe here. So you can see it on the other side. So when I clip, I use a stereoscope and I put the grid on top with the carbon side facing up and the grid bar side facing down, because that's how it's loaded in the aquilose with this side. That side being the mill side. So I use the stereoscope and I orient the grid so that the grid bars are parallel to the notch, and this will just help for when you put it in, your squares may not always be like super nice and flat, so you're able to move around the area that you're going to place your lamella. So I think that's super important. It was pointed out that technically diamond shape would be the best because it would allow you to make a longer lamella. But once you move it to the right or the left, you start hitting grid bar within your pre-cuts. So you don't have enough wiggle room with the diamond unless you're like super sure for some reason that your surface is like pristine. And that's just how the grid looks after clipped. Okay, so just to mention 2 things that we currently have that make our lives much easier for fib milling is the Delmic ice shield and this giant sub-angstrom dewar that you could see in comparison with the 35-liter dewar that's normally given with an Aquilus 2. So on the left here, we have the Delmic ice shield. So it basically just eliminates highly reduces the amorphous ice contamination that will accumulate on your grid over time while it's in this aquilose chamber. So it's cooled, it goes in at, there's a file that you could tell it what currents to go in at. So I have it go in all the time. So from 10 picoamps, which is the lowest current we currently use, and until the highest. If you have the Thermo Fisher version that just comes with the scope that's like very arbitrary, I think it starts going in at like 3 nanoamps or 7 nanoamps or 5 nanoamps, one of those. So it doesn't go in any earlier than that. So it's not actively blocking your grid. So it's a giant metal piece that's cooled. It has a hole in it so that you can actually FIB through it. It will retract every time you tilt the stage more than 10 degrees, move the stage anytime. Or if you're taking any SEM images, which we currently really don't do anymore besides like doing an atlas or a tile set. And the sub-angstrom doer, we just fill it at the beginning of the week and it lasts pretty much like 4 days-ish. It has a sensor in there that will tell you what the level is. Ours is currently out and I can't get it to work, so I'm just guesstimating, and that's really fun. Because if you don't pay attention, you will have samples just warm up. Okay. Everyone hopefully knows what a FIB SEM looks like. This is just the Aqualos 2. So you have your E-beam, your I-beam, your platinum gas injection system that is applied to your grid for rigidity. So when you mill, you're not milling right into your material, you're milling into the GIS first. So it basically protects your sample. And then we have the sputter coater. It's retractable, insertable. So it goes in, and that's just for a thin conductive platinum layer. So some people use it before that, before GIS, and then we add GIS on top. I've used it without and just used GIS, and the milling is perfectly fine. And you might use it afterwards if you want to put it in a Krios and use like phase plates for your lamella. But you have to get the timing right for your sputter coater, because I don't think all of them are created equal. And you might have too much sputter, too much platinum, and then it's black in the Krios, or you may have I wouldn't say too little, but like maybe it's useless. So you just have to get the timing right for that. Okay, so after we make the waffle and we insert it into the Aqualos, this is what one of them looks like. So in maps, I just take a tile set. So on the left here, that's just it coming out straight from the HPF after clipping. So nothing has been on it. And the right one is after it's been sputtered, GIS coded, and then there's a bunch of pre-cuts there. So a nice thing in maps that you can do if you're doing specific targeting is doing a fluorescent overlay. So normally if we have people who are looking for something super specific, like this example is from Will, who works here, so you could ask him about it if you'd like. But he took some fluorescent images, he labeled all the places that he wanted to mill, hopefully, where his cells were in the correct phase. And then I put it in and did an overlay in maps, and then I could go in, see which ones he picked, and then see if it's actually feasible to mill there. And the feasibility will be, is the surface nice enough to mill, that the squares haven't been broken since then, and it's not too close to a grid bar. And normally this works out fairly okay. Targeting cells is kind of hard because you have to kind of figure out where it is in Z because you don't really know, and that's one of the major flaws with this. So you kind of just mill a large lamella and hope you hit something, and then you will hit the cell, but maybe not exactly what you're looking for within the cell. But ideally, you would have a bunch of cells in your lamella, and then you'll hit it anyway. Okay, so there's a lot of manual preparation that goes into waffle milling, unlike just plunge frozen cells, which basically you just put it in, you sputter coat it, you GIS code it, you take a tile set, you pick your cells, and then you kind of just set it up in Autotem and it goes. So it's, I'm saying it like it's like 2 seconds, but it's a little more tedious than that, but this is way worse. So this takes about 5 to 6 hours to set up for an overnight collection, which is maybe like 12 to 16 lamella based on how Autotem decides to give allocated time with the same template out to each of your steps. So sometimes Autotem decides to add 5 minutes to one of your polishing steps, even if it's the same exact template that you've been using the whole time. So that's really fun. But normally the lamella come out pretty okay. I should mention that for sputter coating and GIS coating, the timings are different for plunge frozen grids and waffle grids. So we do it for longer, both things. For GIS specifically, you will want to apply more because you're going to be milling for longer because you have so much material to mill through. So you really want to protect that. So for Nominal thickness in AutoTem being 100 nanometers, I normally do 2 minutes and 55 seconds of GIS on top, and then I will just step down depending if people want thicker lamella or not. So for 140, I might do like 2 minutes and 45 seconds instead. And that seems to be good enough to just leave a little strip of GIS and not completely destroy your sample. Okay, good. So first thing for a waffle milling is doing all these pre-cuts. So we do these orthogonally to the ion beam. So they're just straight down cuts in the bulk. And this takes maybe like, I'd say 2 to 3 minutes per, depending on how you're doing it. First, you would want to find your grid bar. I think I have it here. Yeah. So this is a square with the pre-cut, it's deselected. And then I have the second image is, again, the square with the pre-cut and another mill box on the bottom, because I can kind of see where the grid bars are, but I want to avoid them. So I always check to see where the bottom one is, and then just adjust my pre-cut right above that and mill there. You don't want your grid bar in your pre-cut for a couple reasons. For the smaller one, which is quote unquote the bottom, but it's actually the top later on. But it's actually the bottom because I do a 180 scan rotation because I can't mill through the ceiling. It doesn't make any sense. That one, if you cut through it, that's there for when you actually put it into the Krios and you're doing your tilt. So if you have grid bar at that end, when you tilt to the higher tilts, you're gonna run into the grid bar. And that's unfortunate. So you want that one to be like fairly large, but not too big. So that's why it's smaller than the topmost one. That one is for convenience. So later on, we're going to be turning it back around, tilting, and doing these pre-cleans, which looks like this. So it's basically getting rid of all the bulk material that's underneath the lamella, and you have to tilt, I'd say fairly high, like 40 degrees milling angle, in order to see the bottom. If your sample is even thicker than this one happens to be, then you might have to tilt even higher than that. But if your pre-cut, that longer one, is shorter, you might not be able to see the bulk at 40, so no matter what, you'd have to tilt higher in order to see the bottom. And we're getting rid of this just because, obviously, if you mill a lamella and there's a ton of stuff underneath, what's going to happen when you put it in the Krios? You're not going to see anything, and then you just wasted your time. So we have to get rid of everything so that we don't have any material underneath the lamella. And to do that, normally I do it in tilting steps. So I'll go to 41 degrees because that's what AutoTem kind of gives me after I do a eccentric height. 41 degrees, you could see the bottom. I place the mill box. I can see it clearly here. I mill away all that material. Once that's done, we tilt to 30. So maybe 10 degree increments, and you do exactly the same thing, and you could see the bulk there, so then it goes away, and then I'll tilt to the milling angle, which we currently use is 20, and get rid of all of that material as well. So then you should be left with this, which is, your lamella area, nothing underneath it, which is good. And then you will mill your notch. So this notch is specific for bulk material. It's for stress relief. So basically what happens is that you have your lamella attached only on one end, and you have the bulk material all the way through the lamella like this, kind of like cradling it in a way, but there's a gap, right? So it has the ability to just flex like this. Instead, if you don't have it like that, it will go like this, and that's called buckling, and that's not great. Okay, so that's all pretty simple, right? And then you throw it into AutoTem. So normally I do eccentric tilt, and then I'll do the pre-cleans and the notch, and then I will do the milling angle and the lamella placement just like this. So the lamella goes right in the middle of the notch. You can adjust the thickness to be whatever you like. This one just so happened to be 150. Sometimes users like to have the lamella be thicker to include more material. And that's way more important than getting it thinner and including less material and maybe missing their target. So I place it like this. The overlay boxes, like the blue boxes, are for the rough mill, and then there's like a line here. Can you see the mouse? No. Okay, anyway, there's a line there, and that's just like the overlay. So it's gonna go in steps basically until the end. not very large steps, but your final lamella obviously is the yellow line, and then the overlay part is what's sticking out from there. So I normally move it so that it's kind of over the notch so that I ensure that there's actually separation. And then the milling and thinning, I just have a template that I use. If you'd like it, I think we have it in our waffle protocol on bioprotocol. And that was the one from a couple months ago that I've been using. So I think it's okay to use. But that was after a lot of pain and suffering. No, I'm just kidding. It wasn't that bad, but it was a long road to get to where we got a good template. So very fast milling. So obviously it doesn't happen this fast. This is sped up, but it's just a quick video of what AutoTem actually does. And then you're left with a lamella. Nope. Okay, great. So this is an example of one of the lamella that we will get afterwards. So it looks super nice and thin from the FIB view, from the overview of the SEM. You can't really see any features, but there's stuff there, trust me. And you could see that the leading edge just has a bit of GIS left, which is good enough. It could have milled through even longer than what it was and gotten thinner than this, but I think this looks pretty good. Okay, so this is just straight from our waffle protocol, issues that can occur with improper setup. So the first one is the pre-clean. So you have no pre-clean there, so you see all that bulk material right underneath your lamella, completely useless once you put it in a cryos. So it sucks that all that 5 or 6 hour setup would leave you with this if you didn't do your pre-cleans properly. Even if you don't do it as dramatic as this, if you miss any of it underneath, you won't be able to see your lamella. Overmill, I don't consider it as such a bad thing. I'm really cautious. I like to make sure that my rough mill time is enough to get through all the material, no matter how it's milling through. So some cells mill slower than others. So I have just a set rough mill parameter, kind of the boxes where it just goes for maybe like half an hour, and no matter what the material it is, it mills completely through. So I really don't mind the over mill, because what's a couple minutes overnight affecting me? It's not, so I don't mind that. But if you're doing it in person, I guess you can sit there and watch and make sure that it's not over milling. So once the material is cleared away, you could just move on. Another one that I think is important is the incomplete notch. So I think C shows it best. So the notch is still attached there, and then you have the buckling of your lamella because it's not actually able to move because the stress relief isn't actually there because it's still attached. So we also have the template in our protocol of what to use. 2 minutes and 30 seconds at 0.3 nanoamps seems to be good for any kind of material, but also very specific to these parameters. So the gap in between the pre-cuts is 25 microns. The milling angle is 20 degrees. If you're going to change any of this, you have to change the timing of your notch. And another thing that can occur is double lamella. I mean, I haven't had it occur for me, but I know that sometimes AutoTem can just be like spazzy and just move the mill boxes. So I would just make sure that you're not doing anything near the aquilose, like you just walk away, you don't look at it, and it should work out perfectly fine. It's like a jinx thing. So I never watch it after I submit. Okay, what can we waffle? So I just have some videos here. So this is just yeast, obviously, and some chromosome assembly during yeast replication. We've done plant cells. So this is plant cell wall synthesis. And this is the example of purified protein, which is just 70S ribosomes. So it is possible to do this with protein. If your protein keeps falling apart, air-water interface, preferred orientation, all that. This is like last resort, because like this is painful to do, so you don't want to do it if you don't have to, but like if you got nothing else, you might as well try. Okay, and let's see if this video plays. No, cool. So it used to play. I can do it if I can let's see, stop my share, and then, cool. Okay. So this is a cross-section of a flagella from a trypanosome. We just thought it was super cool. Reza just put it in this Tomo Seg-Mem TV thing that just auto segments all of this stuff. And I think it's just pretty cool because you could see all the membranes and the signaling and the microtubules that are in there. So I thought that was pretty sweet. And it's just kind of a cool end video. And this was obviously from a lamella from a waffle grid, which is the only reason I would include it. Okay, let's get back to this. So that's basically the end. I've included all the QR codes for everything super important. The topmost one is the most important because it has very good details and videos on how to do waffle method from actually using the HPF all the way to the milling. So if you have any questions after you read that, feel free to email me. Yeah, and that's it. And it includes our website, the waffle paper, cryoET portal, if you decide that you have a project that you want to apply for. NCITU if you want to do waffle, anywhere else if you want to do anything else. Like lift out, don't apply here. Thank you. No, I'm just kidding. That's all. Nice, 33 minutes. I try to do this fast so that we actually have time to do more things for HPFing, and then I could show you clipping since it's different. So I thought that was way more important to do a hands-on practical than me talking for another half hour. Any questions? You could also ask later. No, Alina. Yes, Alina.
Birthday.
Oh, thank you. Okay. That wasn't a question. Yes.
Can you work with adherent cells with
So that's one of the issues. So I know Reza tried, Reza's not here, just having the cells on a grid and then applying buffer and just HPFing it. And I think it worked, but if you don't have to do it, then don't do it.
Yeah, so actually Reza did something even more fun.
Oh, did he?
He did primo micropatterning. So he had like clumps of cells in the middle of each square.
That's true, and then he HPF'd
and
it.
then he put the buffer layer on top and HPF. So, yeah, that worked.
Yeah.
Yeah, I'll have an image.
Would would a monolayer of let's say million cells, it's actually at the bottom, right? So you have to have a very flat lamella to even reach it, I guess. The scale is,
You could just adjust your angle. So 20 degrees most likely will hit it. You could just do higher if you wanted to. You just have to make sure that your cuts are longer.
so you can still capture the top.
I think you could still capture it. Yeah, you just have to wiggle it around a bit, adjust the parameters a bit. But you could also talk to Rez about specifically what he did, because I didn't do it. So I don't want to completely speak for that. Great, we're done. I will show you later. No, I use a stereoscope, so I put it in the regular clipping station. So after I mark it with Sharpie, so I can see where the notch is when it's in the proper orientation, you put the grid on, you look in the stereoscope, and with tweezers, you just move the grid.
But they are still immersing
Yeah, yes. So sometimes it moves. So the way we have our setup right now is that our stereoscope has like this little lip, that like a platform that you have to put the clipping station on. So I have to lift it up and move it, do it, and then slide it off really gently in order to actually access the middle part for clipping. So that's a slight flaw, so we can figure it out later maybe. But most of my grids are parallel or just slightly off, which is also fine. And then you get the occasional one that it just completely turned and you're like, whatever, there's nothing to do about it. If you're a super stickler, you could just unclip it and reclip it, but I think it's not worth it. And yes, you can unclip and reclip grids. Okay, officially, yeah.
What's your success rate with non-including a grade?
100%. No, seriously, every time I've done it, I mean, one of them was already like messed up and like it was almost impossible to get it out. And then like it was still messed up afterwards. So I was like, it wasn't me, like it was already messed up. But all the other ones, like I accidentally once clipped all the, I think they were waffle grids improperly. So I put the carbon side down. So when it went in aquilose, I was faced with the carbon side, which I wanted the opposite side. So I went and I unclipped all of them and reclipped them and they were fine. It's just tedious, but it could be done. Okay, officially done.